Hi there. So I think we're all familiar with the deluge of videos in which mathematicians spend 10 to 20 minutes evaluating some integral or some sum or the other. But even still, today we're going to be unapologetically adding to that catalogue of videos by evaluating the first integral from the book Almost Impossible Integrals, Sums and Series by Cornel, Valean. And I do hope I'm pronouncing that correctly, although I suspect I'm butchering it horribly. If you're unfamiliar with the book, I highly recommend it. It actually caught my attention because the foreword was written by Paul Naheen, who himself has written a fairly famous book on fun integrals that I again strongly recommend. I'm going to treat this video as the first in a series of videos evaluating every integral from the book, the book by Paul Valean, and I hope I've justified doing so, even knowing that many similar videos and video series exist in the following three ways. Firstly, integrals are fun, okay? I enjoy watching content creators evaluate integrals, even integrals that I've seen many times before, and I just hope that people maybe get something out of watching me do some of these integrals, even if they might have seen them before elsewhere. Secondly, and probably more importantly, I'm going to approach these integrals in a slightly different way. I'm going to be very candid about the fact that I've seen these integrals before. That being said, the focus will really be on pointing out how one might approach such problems had they not seen them before. In this way, I hope to inspire people to try solving these problems themselves before looking at the admittedly very detailed solutions that make up more than half of the book. Because I think you'll find that many of the problems really don't rely on much more than the 5 or 6 tricks one learns for evaluating integrals at the end of high school, or perhaps in the first term of a course in engineering or the physical sciences at university. Finally, and probably most importantly, I'll aim to spell out in some detail any techniques, formulas, and concepts that can't usually be considered elementary. For example, the definitions and properties of some special functions that don't usually appear until slightly later in the career of a mathematician or physical scientist, and formulas that are less commonly written down full stop. With that being said, and without further ado, let's jump into the first integral. Okay, so this is the first integral from Mr. Valean's book, entitled A Powerful Elementary Integral, and it is as follows. We write I is the integral with respect to x of 1 over 1 plus xy root 1 minus x squared. So this is the integral we're going to evaluate. Now, really, looking at this, my attention is first drawn to this motif here, so this little motif here. And the reason is because this root 1 minus x squared is kind of reminiscent of this identity that cosine squared x is equal to 1 minus sine squared x. The reason is because if I were to say we let x equal, the sine of a new variable u, then when we differentiate it, we'll find that dx is equal to the cosine of u du. And then, just as we discussed before, we use the fact that this little motif here is reminiscent of this identity here to write that the square root of 1 minus x squared is just equal to, well, the square root of 1 minus sine squared u, which is just equal to the square root of cosine squared u, which is of course just equal to the cosine of u. right? And we'll find a cosine in the numerator for the dx and a cosine in the denominator for that root 1 minus x squared, which will cancel each other, right? So immediately we've gained vast simplification, and I'll just notice here that I forgot the limits on our integral here. Silly me, the limits go from 0 to 1. Well, now we need to change the limits, okay? So we have that x is equal to sine u. This is the same as the statement that u is equal to the arc sine of x, okay? So when x is equal to 0, this means that u is equal to arc sine 0. And we know that sine of 0 is 0, so that's 1. Sorry, please give that 0, of course. And when x is equal to 1, this means that u is equal to the arc sine of 1. And of course, we know sine of pi over 2 is 1. So of course, u is equal to pi over 2 at that upper limit. Okay, and it's worth also maybe simplifying that 1 plus xy that appears in the denominator. Well, that's clearly just going to be 1 plus y sine u. Okay, so we've got all the ingredients here for our substitution. So we're going to rewrite our integral as I is equal to the integral from our lower limit 0 up to our upper limit pi over 2. And we are integrating with respect to x, but dx is equal to cosine u du. Our 1 plus xy became 1 plus y sine u, and our root 1 minus x squared became the cosine of u. And just like we promised before, we end up with this little bit of cancellation here, and our integral simplifies to become the integral from 0 to pi over 2 with respect to u of 1 over 1 plus y sine u. Okay, very good, but now how do we proceed? Well, this here is, well, what I always learned as a rational trigonometric integrand, and we use what I learned as the tangent half angle substitutions. I think some places people like to call them the Weierstrass substitutions, but essentially what it boils down to is whenever we have a rational trigonometric integrand, that is a ratio of sinusoids, so a ratio of sines, cosines, and tangents, it's convenient to make the substitution t is equal to the tangent of half the variable, so the tangent of u over 2, okay? Worth finding out what dt is. So dt is the derivative of tangent is secant squared, but we have to use the chain rule here, so we have to differentiate the u over 2 first. So we differentiate u over 2 with respect to u, we come up with a half, and we end up with the derivative of tan, which is secant squared u over 2, and of course we need to put in our little du there. And again, we can simplify this one more time. We end up 1 over 2, 1 plus tan squared u over 2 du. Here, all we've done is we've used the identity that 1 plus tan squared x is equal to secant squared x. Just comes from taking the identity sine squared x plus cos squared x equals 1 and dividing both sides by cosine squared of x. But here, I think you'll notice that tan squared u, well, we defined tan u over 2 somewhere else. We defined it here. So that means we can just replace this with t squared. So we end up with 1 over 2 times 1 plus t squared du. And because we want to convert du into dt, it would help if we actually wrote this the other way around and we divide through by that 1 plus t squared over 2, and if we do that, we'll come up with du is equal to 2 over 1 plus t squared dt. And now, well, we'd be within our rights to ask, what good does that do us? Well, what the good that it does us is that we actually get a lot of simplification if we write the sine of u in terms of this t, this tangent half angle variable. So to do that, we're going to write sine of u. Well, that's just equal to sine of u over 1. And 1 is equal to, well, we're going to write sine of u. Well, first, let's convert the sine of u in terms of tangent half angles. And the formula we're going to use is that we know the sine of 2x is equal to 2 sine x cos x. But if we were to ask for the sine of x, we'd actually end up with half angles on this side because we get 2x here, we get an x here, meaning that in our formula here, we're going to come up with 2 sine u over 2 cos u over 2. And on the bottom, we know that 1 is equal to sine squared u over 2 plus cos squared u over 2. And it's worth here dividing the top and the bottom by cosine squared u. And when we do that, we're going to cancel the cosine u over 2 on the top, and we'll have one cosine left over. So we'll have sine u over 2 over cos u over 2, which will be tan u over 2, which of course we defined before as t, right? And again, we're dividing the bottom by cos squared, so we'll have sine squared u over 2 divided by cos squared u over 2, which is of course t squared, right? And the cosine squared u over 2 is just going to be divided by the cosine squared u over 2, which will give us 1, okay? And I, of course, think we prefer to write that as 2t over 1 plus t squared, just to match how we were writing it for our du variable, for our du expression over there. Very good, but what we really want is 1 plus y sine of u. So it's worth writing that if this object here is sine u, then we can write 1 plus y sine u is equal to, well, 1 is 1 plus t squared over 1 plus t squared. I think we can agree on that. Plus, well, we want y times sine u, so we're going to end up with 2yt over 1 plus t squared. Now we can combine the numerators of these two expressions, so we end up with t squared plus 2yt plus 1 over 1 plus t squared, okay? Now we just substitute these back into this integral over here. First, we need to change the limits, of course. I almost forgot to do that. Well, we are going to say when u is equal to 0, t is equal to tan u over 2, and 0 over 2 is 0, and the tangent of 0 is, of course, 0. And when u is equal to pi over 2, we have t is equal to tan u over 2, and u is pi over 2, so that's going to be pi over 4, right? And, well, to work out pi over 4, these are things I never really remember. Perhaps I should have stored them in my head. But if we draw a little square, well, the triangle you get from cutting a square in half, we can say these sides are equal, and we might as well call them 1. And we just put this angle here. This is pi over 4, otherwise known as 45 degrees, right? Because we've cut a square in half. Well, we have the adjacent and the opposite. So the tangent of this pi over 4 is opposite over adjacent, which is 1 over 1, otherwise known as 1, right? So we have the limits there completed. Now we are completely in a place where we can just write down this integral as the integral from, well, it's from 0, our lower limit, to 1, our upper limit. And we found out that 1 over 1 plus YSU, or we just Y sine U. We just have to flip this fraction here, so we end up with 1 plus t squared on the top divided by 1 plus 2yt. Was it plus t squared? Yes, it was plus t squared. And dt was 2 over 1 plus t squared dt. Sorry, excuse me, this was du. So just to kind of be very clear about where we got these expressions from, this guy here was just our du, and this guy here was our 1 over 1 plus y sine u. Okay. We get some nice cancellation here of the 1 plus t squareds, and we can pull the 2 to the outside of the integral. So if I write that by cancelling this and putting a 2 on the outside, we end up with the nice simplification that I is just equal to twice the integral from 0 to 1 of, we have 1 over 1 plus 2 yt plus t squared. So we'll write dt over 1 plus 2yt plus t squared. Okay. We can do a little better than this, because this on the bottom is a quadratic expression, and for integrals like this we want to complete the square. Okay, so we want to complete the square. And I think you'll agree that on the bottom, well, what we have to do to find our completed square expression is we take our t, because it's a polynomial in t, and we add half the coefficient of t in the expression, so plus y squared, and of course we have our 1, our constant, but then we have to subtract off our constant term squared, or constant, because y is a constant there, it's a parameter, so it can vary, but as far as we're concerned for this integral it's a constant. But here we just write, we need to pick off our y squared, and just to make sure everything's in order, when we expand this we're going to get t squared plus y squared plus 2yt, because this is our completed square form, but we had a stray y squared that we didn't want. That gets cancelled by this. We end up with 2 terms plus the 1, which is everything we have here. Okay. Very good. Now we just make our nice substitution, because if I'd like to just remind you that of course this is from 0 to 1, the integral, you might know that the integral of 1 over 1 plus x squared with respect to x is equal to arc tan x, right? So I think if I let this t plus y, if I let that equal the square root of 1 minus y squared, 1 minus y squared tan theta, so our new variable, we already changed to u, so we'll use theta for this variable here. I hope you can see what's going to happen here. If I square this expression, I'll come up with 1 minus y squared tan squared theta times 1 minus y squared, and I can pull out a factor of 1 minus y squared, and I have 1 plus tan squared theta, but we know what that simplifies to. That's supposed to secant squared theta, and when we differentiate it, tan becomes secant squared, so we'll end up with cancellation again from the top, between the top and the bottom. I know that was a little bit quick, so we'll do it again, but a little bit more slowly, just so we can see what's going on. Firstly, we want to find dt and the limits, so dt is just equal to root 1 minus y squared secant squared theta d theta, and to find the limits we're going to say when t equals 0 we end up with y, because t is equal to 0 here, is equal to root 1 minus y squared tan theta, and of course if we divide both sides by root 1 minus y squared and take the inverse tangent or arc tangent, we find theta is equal to the arc tangent of y over root 1 minus y squared. I'm just going to put a little bracket around that so we have a nice expression there. And when t is equal to 1, so that's the upper limit of the integral, we have 1 plus y is equal to the square root of 1 minus y squared tan theta. This is the same as the requirement that theta is the arctangent of 1 over y, or sorry, 1 plus y over root 1 minus y squared. So that's the arctangent of 1 plus y over root 1 minus y squared. And I think you might be able to see a simplification we can make here, but I personally think it seems like we might do better if we keep these guys very similar. So let's just crack on and proceed, because we can't perform the same simplification here, but we could here. But it would be nice if the limits were just similar like that. Next, we're going to simplify the integrand. So we're going to write that t plus y squared plus 1 minus y squared. Well, that's just going to be equal to the square of our t plus y is just 1 minus y squared tan squared theta plus 1 minus y squared. We can factor out a common factor of 1 minus y squared. That's going to be 1 plus tan squared theta. And we've seen that identity before, that 1 plus tan squared theta is just equal to secant squared theta. So we end up with 1 minus y squared, 1 minus y squared, secant squared theta. And now we have all our ingredients here, so we're just going to put them into the integral. Well, I is equal to something that looks quite ugly, but if you bear with me, you'll see it's not actually that ugly. The lower limit is going to be, well, the upper limit, because we just started writing it, is arc tan 1 plus y over root 1 minus y squared, and the lower limit was arc tan y over root 1 minus y squared, and we are integrating it. Well, we look what we are doing, and we have dt is root 1 minus y squared secant squared theta d theta, so we have root 1 minus y squared secant squared theta d theta divided by, it was 1 minus y squared secant squared theta. Now there's some very nice simplification that happens here. Firstly, the factors of secant squared theta cancel. Secondly, we have two factors of root 1 minus y squared on the bottom and one factor of root 1 minus y squared on the top. So we can cancel that, meaning we'll have to square root this. And then, well, this is a constant because we're integrating with respect to theta, and y does not depend on theta. So we can pull out our and I think I've actually dropped a factor of 2 here, so I can just put the factor of 2 back in here, and we end up with 2 over root 1 minus y squared, the integral from, and I'm just going to copy these to avoid having to write these again. So this is our lower limit, and this is our upper limit. And the only thing that's left here of the inside of the integral, that's just our d theta. But really that's just going to be theta evaluated at the top and the bottom. So it's going to be, and of course, let's just write this, arctangent. So we're going to have 2 over root 1 minus y squared. And it's going to be arctan 1 plus y over root 1 minus y squared minus arctan, make sure I've got the limits the right way round, and yep, upper limit is this, there we go, arctan y over root 1 minus y squared, just like that. Now, if you can see here, this no longer depends on x, and we don't have any more integrals to evaluate. So we're done. Essentially, that's the answer. We are completely done with this integral, and we could stop if we wanted to. However, it's worth pursuing the answer just a little bit more carefully and just seeing if we can do a little bit better, because you see we have two arctangents here, and perhaps maybe we suspect there's a less commonly known way to combine arctangents, and let's see if we can find such a way. Well, let's define Z. We'll define Z as arc tan A minus arc tan B. Remember, we are trying our best to simplify the difference between two arctangents. So we're going to name that B. And if I can just remind you of our compound angle formula for arctangents, we have arc tan, let's say A plus B. Well, that's just going to be equal to, oops, sorry, other way around. Sorry, this is our compound angle identity. So it's going to be tan. It's going to be tan, let's say tan x plus y. So tan x plus y, well, that's just going to be tan, and of course we want to, let's just do both of them at once. So it's tan plus or minus xy is tan x plus or minus tan y divided by 1 minus plus tan x tan y. And of course, it's not difficult to find this, because all we do is we use the compound angle identity for sine on the top, the compound angle identity for cosine on the bottom, and we divide through by cosine squared. Oh, sorry, by cosine x, cosine y, and we'll end up with a nice formula here, okay? I personally don't remember this. I always kind of almost do this in my head, where you know what this looks like, and you know what will come out as when you divide it by sine x. By cosine x, cosine y. Very good. So now we are going to take the tangent of z, and I think you're going to see what will happen when we do that. So the tangent of z is the tangent of arc tan x, sorry, arc tan A minus arc tan y, but we have a formula for this. We have this formula for the tangent of the difference between two things, because we have plus goes with plus, minus goes with minus, so we are going to have, we're just going to have tan A minus tan B divided by 1 plus tan A tan B, right? But well, so the tangent of arctan, so that's not going to be, sorry, you're not going to have tangent at all. What you're going to have instead is you're going to have A minus B over 1 plus AB, right? And of course now we can just say Z is equal to the arctangent of both sides, so it's the arctangent of A minus B over 1 plus AB. And look here, what I've done is Z is this expression here, and I found a way to put them together, right? So we have an arctan A minus arctan B here, and now we have an arctan of some function of A and B, okay? So we found the formula we were after. Well, it looks like we're just going to have to subtract these arguments to arctangent here, and divide them by 1 plus the product of these arguments here, then they take the arctangent of the result. So I think you can see that our integral I is just going to be 2 over root 1 minus y squared arctangent, and let's make a big bracket here for their difference, which is 1 plus y over root 1 minus y squared, so 1 plus y over root 1 minus y squared, and we're subtracting y over root 1 minus y squared. The whole thing is to be divided, by 1 plus their product, so 1 plus y over root 1 minus y squared times y over root 1 minus y squared. Very good. So now we can combine these together. So we think of cancelling the y's because these have the same denominator, so we'll get 1 over 1 minus y squared in the numerator. I'm going to write that as 2 over root 1 minus y squared arc tan of, well, we're going to have, let's make that a bit bigger, so we're going to have 1 over root 1 minus y squared all over, well, we can see what's going to happen here. We're going to have these collect together. There's a root 1 minus y squared and a root 1 minus y squared here. So that's just going to become 1 minus y squared. And I'd like this to be over the same denominator. So I think you can see that we're just going to have 1 minus y squared, right, plus y lots of 1 plus y, and all of that is going to be over 1 minus y squared. And let's just talk ourselves through that one more time. We talk ourselves through that because these are going to combine together to make the 1 minus y squared, but I'd like it to be over, to combine it with this, so to give this the same denominator as this term here, I'm going to write it as 1 minus y squared over 1 minus y squared, then I'll just add it to y times 1 plus y, and that'll give us the answer. Now, dividing by a fraction is the same as multiplying by the reciprocal of that fraction, so very easy to write this as 2 over root 1 minus y squared, the arc tangent of 1 over root 1 minus y squared. And let's see if we can simplify this before we drag it over. Well, here we have a y times 1 plus y times y, so it's going to be y plus y squared, but we have a minus y squared here, so we can cancel these two guys here, and we're just going to have a 1 plus y left over, so we're going to have here, so it's 1 plus y in the numerator, but remember, we're dividing by a fraction, that's the same as multiplying by the reciprocal, so we're going to have a 1 minus y squared over our 1 plus y, and we are essentially done at this point. So now we just have to maybe get some cancellation going. Well, this is 2 factors of root 1 minus y squared, so I can rewrite that as this. And here we have something that looks a decent bit more simple. 2 over root 1 minus y squared arctangent, and we're going to have root 1 minus y squared over 1 plus y. Okay. Now, I think it's a good idea to just kind of maybe go one step further with this simplification, because we know 1 minus y squared, that's just the very same as 1 plus y times 1, so let's see, times 1 minus y. And we want to have 1 minus y squared divided by that, and we'll see kind of what we get if we do that. So we are going to have the square root of this, of course. So we're square rooting this, we're square rooting this, and we're square rooting this. And I think you can see we're going to get rid of that factor of 1 plus y, and we're going to have a square root left on the bottom. So just to kind of drive that point home, we're going to have 1 plus y is the same as the square root of 1 plus y times the square root of 1 plus y. So if we were to divide them, we would end up cancelling one factor of the square root of 1 plus y between them. And I think you can see that means our integral becomes reduced to 2 over root 1 minus y squared, the arc tangent, and what's on the top? We have our root 1 minus y over 1 plus y, okay? And personally, I would stop here. Well, in the book I did stop here, but when I compared this to our answer, well, the answer in the book, it was a little bit different. There was the arc sine of something here, something more simple, which essentially just led me to think, well, there must be some way in which the arctangent of this complicated looking thing is just the cosine of something simple. So let's kind of go back to the drawing board. Well, our inspiration for searching for a simpler form for this solution comes from this identity here, that 1 plus tan squared x is just equal to, instead of secant squared, I'm going to write 1 over cosine squared. Okay, so I'm writing that as 1 over cosine squared. I'm going to change that into red here. Very good. And here, but also notice this 2. This 2 is what I'm very concerned with, because we know that the cosine of a double angle, the cosine of 2x, is just equal to cosine squared x minus sine squared x, and we can write that as 2 cosine squared x minus 1. So it's kind of, again, this is more of an inspiration thing. I just want to say the way that I personally would think about this. We see a cosine to something here, we see twice something here, and we see this becomes cosine squared, but we see there's a way to convert a cosine to a tangent, which we expect to undo this arctangent, okay? So essentially, this just leads me to essentially just write an expression for the cosine of this thing here, okay? So I'm going to write that essentially z is just going to be equal to the cosine of this whole thing here. So the cosine of this whole thing here. Well, let's go ahead. So we're writing the cosine of twice the arctangent of the square root of 1 minus y over 1 plus y. And, well, how can we simplify that? Well, we simplify it by using our double angle formula here. So we write the cosine squared of root 1 minus y over 1 plus y. And of course, we won't forget to subtract our 1, and we need 2 of these, of course. Is that correct? Have I botched something here? Nope, I have not. That's absolutely correct. Well, now what do we kind of do next? Well, sorry, and again I've botched this horribly, because this is not root 1 minus y squared. This is the arctangent of that. So I'm going to write that as arctan, and let's not forget our bracket there. Very good. So now, well, this is cosine squared, and again, remember that cosine squared can be, well, 1 over cosine squared is 1 plus tan squared x. Of course, that doesn't make sense, so I should write cosine squared x there. Please excuse me. We're going to write this as 2 over 1 plus tan squared arctan root 1 minus y over 1 plus y. And let's move this further to the center, and we subtract 1. Very good. So now we can, well, tan of arctan is like we did nothing overall. We took the tangent and the arctangent. They're inverse functions, so overall we did nothing to that root 1 minus y over 1 plus y. So we are within our rights to write this as 2 over 1 plus the square of this, which is 1 minus y over 1 plus y minus 1. I think you can see this is starting to take shape. So we multiply the top and the bottom by this 1 plus y, so we end up with 2 plus 2y, all divided by, well, we're going to have 1 plus y plus 1 minus y minus 1. We end up with cancellations of the y. Let's see, have I done anything horrible? here? I have not, because now I think you can see, let's go to a new page, I think you can see that our z is just equal to, well, this is 2 plus 2y, 2 plus 2y over 2 minus 1, which is equal to 1 plus y minus 1. Of course, the 1's cancel, and our z, which is equal to, remember, it's our cosine of 2 arctan root 1 minus y, so we're going to write the cosine of the arctangent, sorry, twice the arctangent of root, I think it was 1 minus y over 1 plus y, 1 minus y over 1 plus y, and that's just equal to y, right? So if we take the arc cosine of both sides, we have 2 arctan root 1 minus y over 1 plus y is just equal to the arc cosine of y, right? And again, I just want to say that really we were inspired to investigate the cosine of this thing by appealing to these two formulas here, and it paid off because we found a tremendous simplification. We found that twice arctan the root of 1 minus y over 1 plus y is just the arc cosine of y, which is much, much simpler in my opinion. And now we are within our rights to write the final form of our integral in all its glory. That's just going to be the arc cosine of y, all divided by root 1 minus y squared. I'm going to put a little red box around that just to delimit that as our answer. So just to go back, our integral up here, that's a lot of pages, but our integral started off life here as this definite integral from 0 to 1 with respect to x of 1 over 1 plus xy root 1 minus x squared, and we came up with this surprisingly simple answer of arc cosine y over 1 minus y squared. Okay. Thank you for watching, and I'll see you next time.